SJ Institutes of Engineering and Technology. In the current video lecture series, we are studying the subject of Physics Group 1. Till now, in this chapter of the wave motion and acoustics, we have learned about the types of waves, types of wave motion, classification of sound waves, classification of musical sound, and characteristics of musical sound. In current video, we are covering the topics such as sound absorption and reverberation. So this seems to be quite very small topic, but in that we will learn about what is sound absorption, properties of sound absorbing material, what is reverberation and what is reverberation time and how to calculate it, what is absorption coefficient and how it is related to the reverberation time will also be discussed, and Savant's formula, that is the correlating formula between the absorption coefficient and reverberation time, will also be discussed. At the end, we will see one numerical example of that. So let us start with the first topic, that is sound absorption. So the room acoustic describes how sound behaves in a space. That means the listener and the sound source are in the same room. If the room has nearly no sound absorbing surface, that is the wall, roof and floor, the sound will bounce between the surfaces and it will take a long time before the sound dies out. If the listener is kind of a room, will have a problem registering the speaker because he hears both direct sound and the repeated reflected sound waves. If the surfaces instead are covered with a sound absorbing material, the reflected sound will decrease much quicker and the listener will only hear the direct sound. Also, the general sound level in the room will be decreased. So, here are some sound absorbing materials with their properties. So first one is the porous absorbent. So whenever a sound wave strikes the surface of a porous material, a part of a wave gets reflected while the other part enters into the porous material. The part of the reflected wave energy is reduced while the part of a wave entered into the material is converted into the heat. So examples of porous materials are rockwood, wood wool and the glass silk. Okay. Now next are the cavity resonators. A cavity resonator is a chamber having a small opening for the sound waves to enter. When the sound waves enter the resonator, due to the multiple reflection inside, the sound waves are absorbed. They are, for example, the air conditioner plants and some special machines, etc. Third one is the resonant members or the panel absorbent. The absorbent material is fixed on a framing with an air space between the framing and the wall. When sound waves strike the panel, due to the flexure vibration on the panel, certain amount of sound energy is absorbed by the panel, which is converted into the heat energies. Examples are wood doors, gypsum boards are some of the examples of this. Now, the fourth one are the composite absorbers. A composite absorber is a single unit which does the function of the other three absorbers. It is a combination of all three listed above. It consists of a perforated panel fixed over an air space containing a porous absorber. When the sound waves strike the panel, they pass through it and damped by the resonator of the air in the cavity. So this is how the sound is being absorbed in the room, and thereby the listener is able to hear the speaker. Okay. So materials A material's sound absorbing properties are expressed by the sound absorbing coefficient small a as a function of frequency, a range from 0.0 to 1.0, from the total reflection to the total absorption. Acoustic absorption refers to the process by which the material's structure or the object takes in the sound energy when the sound are encountered, as opposed to the reflecting the energy. Part of the absorbed energy is transformed into the heat and a part is transmitted through the absorbing body. Now, next topic is reverberation. The persistence of a sound in a hall after the source of sound is cut off is known as a reverberation. Reverberation takes place due to the reflection from walls, floor, ceiling, and other reflecting surfaces. Due to these reflections, the sound is heard for some time after the source is cut off. Next is reverberation time. When a source of sound is cut off, the sound intensity decreases. The time taken by the sound to fall to the minimum audible level after the source has been cut off is known as a reverberation. It is different from the echo. Echo is a reflected sound, but it is the source sound. Okay? Remember that thing. So Sabin found that the sound from an organ pipe of about 512 Hz became inaudible when an intensity fell to 1 millionth of its original intensity. Hence, reverberation time can also be defined as the time taken by the sound intensity to fall to the 1 millionth of its original intensity after the source has been cut off. Okay? So that is the definition of reverberation time. Reverberation time. Reverberation time can be defined as time taken by the sound intensity to fall to the 1 millionth of its original intensity after the source has been cut off. So Sabin's formula is the next topic. Sabin's formula gives the reverberation time of a sound in a hall in terms of volume of the hall, absorption coefficient of the sound, and absorbing material and the surface areas. So the following assumptions are made in the derivation of the Sabin's formula. The first assumption is sound travels with the same velocity in all the directions. Second is absorption of sound is in the air is negligible. Third is the sound energy is uniformly distributed in the hall. So, according to the Sabin's formula, the reverberation time T is given by T is equals to 0.161 V divided by sigma AS, where V is the volume of the hall, sigma AS is the total absorption by the sound absorbing materials in the hall. That is given by A1S1 plus A2S2 plus A3S3 and so on, where A1, A2, A3 are the coefficient of absorption of sound absorbing material. S1, S2, S3 and so on are the surface areas. So Sabin's equation provides the most accurate result when the average absorption coefficient is less than 0.2. In this respect, the effect air absorption is neglected above 4 kilowatts. So this is classical and the oldest reverberation time equation developed by W.C. Sabin. Okay, so the derivation part of the equation is not included in our syllabus. It will be studied further in the acoustical engineering. Okay, but our aspect over here is just to know the formula of reverberation time. So next topic is absorption coefficient and its calculation, okay, or determination. So let us first of all define absorption coefficient and then after we will determine its value. So absorption coefficient of any material for the sound is defined as the ratio of sound energy absorbed by the material to the total sound energy incidented on it. So absorption coefficient A is equals to sound energy absorbed by the material divided by the total incident sound energy. The absorption coefficient is also defined as open window units OWU or Sabine by comparing the absorption of sound by surface with the absorption by an open window of 1 meter square area. The absorption coefficient is of a material in OWU or Sabine is defined as the reciprocal of the area of sound absorbing material which absorbs the same amount of sound energy as that of absorbed by the open window of area of 1 meter square. Now, how to determine absorption coefficient? Let us see that. The absorption coefficient for any material is found by the first measuring the reverberation time in a hall and then measuring the reverberation time in the same hall in the presence of the sound absorbing material. So let us take T1 is equals to the reverberation time in a hall without the sound absorbing material. So T1 is equals to 0.161 V upon sigma AS. Now where V is the volume of the room. Now let us add sound absorbing material to the room. So T2 is equals to the reverberation time in the hall in the presence of sound absorbing material. So S1 is the surface area of the sound absorbing material and A1 is the absorption coefficient of that material. So T2 is equals to 0.161 into V divided by sigma AS plus A1S1. Now over here another surface area of the absorbent material is added to the room. So thereby the total area is increased. Okay, remaining all things is same. Now comparing equation 1 and 2 we get 1 upon T2 minus 1 upon T1 is equals to placing the values we get this equation. Now on simplification we get 1 upon T2 minus 1 upon T1 is equals to A1S1 divided by 0.161 V. So taking A1 as an absorption coefficient as a subject we get A1S1 is equals to S1 upon 0.161 V into 1 upon T2 minus 1 upon T1. So that is the absorption coefficient A1. Now let us see one numerical example for this case. A hall of length 20 meter, breadth 15 meter and height 10 meter has a reverberation time of 2 seconds. Calculate average coefficient of absorption. We need to find out average coefficient of absorption. Okay, so the given data are T is equals to 2 seconds. Now volume of the room, that is length into breadth into height, that is 20 into 15 into 10, that is 300 meter cube. Now let us take a look at the solution part. We know that sigma AS is equals to, we can say that average coefficient into total surface area. Small s over here is the surface area total of the room, entire room, and AAV. A is the absorption coefficient and suffix AV stands for the average. Now, first step is to calculate the total surface area of the entire room. So, room contains total 6 wall surfaces, floor, ceiling, and 4 walls. So, S is equals to the total surface area I have calculated over here, that is of about 1300 meter square. Now T is equals to, this is nothing but the formula of how to calculate the surface area of cuboid. Refer to that if you don't know about this. The total surface area of cuboid is that. Okay. Now T is equals to 0.161 V divided by sigma AS. Substitute the value of AAV into S instead of sigma AS and calculate the AAV, that is nothing but the average coefficient of absorption. So that is 0.16 0.186 OWU, that is open window unit. So now in the next video we will learn about the factors affecting the acoustic of building and its remedies and simple harmonic motion. So that's it for today guys. Thanks for watching.